When we built the momentum equation, one term went by with a promise. The viscous force, mu times the Laplacian of the velocity, came with the words, "That's a derivation of its own. This is that derivation." The starting clue is simple. Pressure is the push a fluid makes straight into a surface, but a moving fluid does more, it drags along the surface too. That sideways drag is where viscosity lives. Put our usual little box in the flow and look at one face. The surrounding fluid pushes on it, and that push is a force in some direction. Pressure is only the part pointing straight in, along the normal. There's also a part pointing along the face, a shear. So to describe the force on a face, one number isn't enough. You need the direction of the force and which face it acts on. That double bookkeeping is the stress tensor, sigma, with two indices, the force direction and the face it pushes on. In 3 dimensions, 9 components. It helps to split that tensor in two. One part is the same in every direction, the isotropic pressure, pushing inward equally. That's the minus P piece. Everything left over, the part that depends on direction, is the viscous stress, written tau. Pressure we already handled in the momentum video. Tau is the new force we're after. Now the same trick as the conservation laws. The stress on the left face and the stress on the right face differ slightly across the small box. Taylor expand the difference, and the leftover, per unit volume, is the rate of change of the stress across the box. Summed over all the faces and directions, the net surface force per volume is the divergence of the stress tensor. Split by the two parts, that's minus the gradient of pressure, plus the divergence of tau. So the viscous force, per volume, is the divergence of tau. Now we just need tau itself. Before the tensor, the everyday version everyone has felt. Imagine fluid in simple shear, the top moving, the bottom still, a smooth gradient of speed in between. Stir honey and water, and you feel the difference. The friction between the layers, the shear stress, is proportional to how fast the speed changes across the gap. Tau equals mu times the velocity gradient. That mu is the viscosity, and the full tensor is just this idea, written for every direction at once. Here's the key physical point. Viscous stress doesn't care where the fluid is, or even how fast it moves, only how fast it's being deformed. Slide a block of fluid rigidly, and there's no internal friction. Shear it, and there is. The right measure is the rate of strain, the symmetric part of the velocity gradient. A Newtonian fluid is one where the stress is simply proportional to that rate of strain, with the viscosity as the constant. The ij component of tau is mu times the gradient of velocity I in direction j, plus the gradient of velocity j in direction I. The everyday shear law is just one entry of this. Now the payoff, feed this tau into the divergence we found. Differentiate the ij component by the j index and sum. The first piece is the second derivative of velocity I, summed over all directions, which is the Laplacian of velocity I. The second piece is the derivative, in the I direction, of the divergence of the velocity. For an incompressible fluid, that divergence is zero, mass conservation again. So the whole second piece vanishes, and what's left is exactly mu times the Laplacian of the velocity. That's the viscous term derived. Drop it into the momentum equation, and the viscous term is no longer a promise. It's mu Laplacian u earned. One caveat: if the fluid is compressible, the divergence of velocity isn't zero, and a second viscous term survives, proportional to the gradient of that divergence. For most everyday near incompressible flow, it's just mu Laplacian u. So the viscous force is the divergence of the shear stress in the fluid. Model that stress as proportional to the rate of strain, take the divergence, use incompressibility, and you land on mu Laplacian u. The Laplacian is the fingerprint. It measures how much a particle's velocity differs from its neighbors, and friction works to erase that difference. That's all for this video. Tell me what you want to see next in the comments.